Good afternoon. I welcome you in several functions. First of all, of course, as rector of the University of Vienna, to the talk of David Hogg on a topic which is also scientifically of a lot of interest to me. Is machine learning good or bad for science? I don't think you will give a definite answer for that, because it's one of the main questions in this field. My other background, as some of you know, is that before I came to Vienna, I was a professor of industrial mathematics, and my field was, I cannot say anymore, is inverse problems for especially systems governed by partial differential equations. And I did a lot of also basic and also industrial work for systems governed by partial differential equations. And then I also tried out, this was 10, 15 years ago, modeling with machine learning algorithms. At that time, I think it was support vector machines. And what we did then is train a support vector machine not only on real data, but also on the results of PDE modeling, which was, of course, much, much slower. So that's my only real experience with machine learning. Of course, I followed the discussion. And the consequence of that experience was also that we, as the University of Vienna, emphasize a lot the field of data science. We have a very good faculty of mathematics, a very good faculty of computer science. We have 20 faculties altogether, some of which currently work also with machine learning algorithms. And we installed sort of a cross-cutting structure, the data science platform. I think Professor Gross will mention more about this. And the aim is, of course, in the end, to solve questions which will never be solved completely, like the one you want to address today. So I'm very glad that you came, looking forward to your talk, and turn over to João Alves. Or Philip Gross.
So, hello everybody, my name is Philip Gross. I'm the speaker of the Research Network Data Science, which is hosting today's event. The Research Network was founded in 2018, and it provides a hub for activities related to data science at the University of Vienna. And what is special about this field of data science is its interdisciplinarity. It heavily draws on several different areas, from computer science, mathematics, statistics, to the humanities, psychology, law, as well as the sciences, physics, chemistry, and so on. And what we really need to make progress in this field is to create an environment where people from different fields can interact with each other, talk to each other, and learn to understand each other. And this is the key mission of the Research Network. And to that end, we are involved in several activities. For example, 3 new master programs that are interdisciplinary across different faculties. A currently running innovation lab on digital entrepreneurship, as well as several social and scientific events, probably the most important of which is our distinguished lecture series, What is Data Science? So obviously different people and different fields have different ideas of what data science is. And our idea in creating this lecture series was to kind of illuminate the question, what is data science, through world-leading scholars, so through the vantage point of world-leading scholars, such as Professor Hogg. And the perspective that we will hear today is the interplay of machine learning and science, and the use of machine learning in scientific discovery, which is a very exciting and flourishing field that has made several important breakthroughs in the last years. For example, the solution of the protein folding problem is one of the key discoveries that this really has a transformative impact on biology and understanding diseases and designing drugs. And today we will hear whether machine learning is good or bad for science, and I'm really eager to find out which one it is. I would also like to say that this is a real special event for me and for the research network. We have been trying to put it together for a while, I think at least 2 years, but we were not successful to do it in presence due to the pandemic. So it's all the more exciting that we made it this year finally, and we could even meet in such a great venue. So I'm very happy about that, and with this I would like to turn over to Joao, who will introduce today's speaker. Thank you.
So good afternoon, everyone. My name is, as you heard, Joao Alves. I'm a professor of astrophysics at the University of Vienna, and it is my great pleasure to introduce today's speaker, Professor David Hogg, as a distinguished lecturer of the Data Science Research Network at the University of Vienna. Professor David Hogg is a mandatory reference in research and methods in astrophysics. He is recognized for his brilliance and creativity in tackling observational and theoretical problems, his broad and deep thinking across the entire field of astrophysics, his commitment to education, and his ideas on the great social challenges we all face, his approachability and his support of young researchers. Few astrophysics in the world have not used one or several of his methods for their own research. Professor Hogg has about 300 refereed papers in astrophysics only, and an H-index of above 100. David Hogg grew up in Toronto, Canada, that he finds similar to Vienna in many aspects. He did his undergraduate studies at MIT in Cambridge, Massachusetts, graduating in 1992. While an undergraduate, he did research and education in robotics at the MIT Media Lab, in solar system research at the Canadian Institute for Theoretical Astrophysics. He then moved to Caltech to pursue a PhD on gravitational lensing and galaxy evolution. His PhD made heavy use of the then new 10-meter Keck telescopes. In 1997, he began a long-term membership at the Institute of Advanced Study, Princeton, where, among other things, he became involved in the Sloan Digital Sky Survey. Professor Hogg then moved to New York City, to New York University, NYU, in 2001, as a professor of physics and data science, and was granted tenure in 2007. His work at NYU has ranged from fundamental cosmological measurements to stellar dynamics, to exoplanet search and characterization. For non-astronomers, this means all of astrophysics. His work includes a significant engineering component in areas of instrument calibration, automated data analysis, and statistical inference. Today, Professor Hogg is working towards several comprehensive projects in observational astrophysics, including the measurement and analysis of every galaxy in the observable universe, above a certain mass, every star in our galaxy above a certain brightness, and every image above some quality taken by any astronomical camera. These are, of course, fantastic long-term goals, but he's already involved in present-day projects that works towards them, which include astrometry.net, which is one of the brainchilds of Professor Hogg, the European Gaia satellite that we know very well here in Vienna, and we are involved, and the Sloan Digitized Sky Survey. Professor Hogg spends part of each week at the Flatiron Institute of the Simons Foundation, this is New York, where he is a group leader, and parts of the summer he spends at the Max Planck Institute for Astronomy in Heidelberg as a visiting scholar. We hope that in the future he will have the University of Vienna as a regular stop during his summer tour in Europe. So David, without further ado, please tell us, is machine learning good or bad for science?
Joao, that was lovely. It's really great to be here, and I hope somebody writes to one of my students and tells them that I am distinguished. because that word has never been used. Okay, good, let's go. So I am going to answer the question, but let me start with something very straightforward. So you may know that the universe is expanding. If you don't know that, that is a very, very important fact about astronomy. It's basically the most confidently known fact in all of cosmology, that the universe is expanding. And the way we know it is you look at the Doppler shifts of distant objects. Distant objects are redshifted, they're moving away from us, and more distant objects are moving away from us faster. So if you run back the clock, the universe in the past was more dense than it is now. Note Austrian content there. Okay, good. Now, another, switching gears, machine learning. What's the first place that I really started to think about how does machine learning relate to science? There was a demonstration a long time ago of finding kittens in YouTube videos. So this is not a made-up example. This is a real example. You have a bunch of videos on YouTube where you know that they contain kittens. Let's find all the other YouTube videos that contain kittens. Good? We're working through the important scientific activities of the Western world. Okay, recommender systems. This is something that you're all familiar with. You are all upset with your social media because it knows that if you're enraged by a certain set of news items, you'll be enraged by new ones, and those are called recommender systems. Good. Okay, now, how was the measurement of how was the expansion of the universe discovered? It was a data-driven discovery. That discovery happened by looking at data. What does the data look like? You notice that the recession velocity of galaxies is related to the distances to those galaxies. And then the slope of the line that relates distance to recession velocity tells you the age of the universe, or tells you the expansion rate of the universe. So the first thing to say is that it was discovered in the 1920s by Hubble and Humason, and they were not trying to predict new data. They weren't using the data that they had to predict new data. They were using the data that they had to understand something fundamental about the universe, which is not directly visible in the data. It's found by an analysis of the data. Good? Okay, good. So what's the difference between the expansion of the universe and finding kittens in YouTube videos? In the case of the kittens example, you're trying to find new videos that will have a certain data property. Some of these videos have the data property they contain kittens, you know that. Some you know don't contain kittens. Now you're trying to find new videos that have this data property. People will say that it contains kittens. Whereas in the expansion of the universe case, you're trying to measure a latent parameter of the universe, something about the universe you can't directly observe, you're trying to measure it using the data. So these two activities have very different goals. One is about predicting new data, one is about understanding the universe, or something with some significance. Okay, good. So what am I going to say? I'm going to say that machine learning provides important tools for the natural sciences. I'm going to give you some examples of work we do with machine learning. I'm not going to talk about data science as a whole. You brought up data science, and it didn't occur to me that I should have a definition for data science, because I think about that a lot too. I was involved in establishing the Center for Data Science at NYU, and so I have feelings about that. But I'm going to talk about, I am going to try and give a little bit of a definition of machine learning, as we'll see in a second. And I think we should use machine learning in the sciences. It is good for science. There's a lot of places where it's made things possible that weren't previously possible. But I'm going to say that I'm not confident that we can use machine learning in certain tasks. There's certain tasks where we might be making a big mistake by using machine learning. And it connects very much to the research you mentioned about differential equations and support vector machines. And some applied math is coming. Okay, good. So now I'm going to try and tell you what I think machine learning is, and I'm actually giving this from the point of view that I assume that most people in this room basically do have a feeling of what machine learning is. I'm giving you my take on it. I'm not really going to walk you through carefully. So I apologize if you came to this talk with completely blank. I apologize. Hopefully I'll give you a sense. Oh, by the way, if you want to take more time with the slides, there's a URL there. That URL leads to the slides. So if you want to go backwards or forwards, you can go backwards and forwards on your phone from that link. Okay, good. Good. So machine learning is a hammer. It's about making very, very flexible models of data, and it performs some tasks very, very well. And I'm going to talk about some tasks. First, let me just say, here's how machine learning is generally used in science, in natural sciences. There's additional things I would add here if you went to some social sciences, and there's different things I would add here if you went to the humanities. But in the natural sciences, there's classification problems where you have to make decisions, you have to make choices in the course of an experiment. And a good example is the Large Hadron Collider. Takes data 10 to the 7 times the rate at which it can be written to disk. If you're taking data 10 to the 7 times faster than you write to disk, you have to make decisions very fast. There's label transfer or regressions where you have some labeled data, like the videos example, you have data labeled kittens, you have other data that are unlabeled. There's that kind of problem. So we use that a lot where we have information about a few stars and we want to label many, many stars. So we know the temperatures, say, of some stars. We want to know the temperatures of all the other stars. There's things like manifold learning, and a lot of people use this in their scientific work because it's a way you can visualize complex data. People use TSNE and UMAP and things like that. I don't know if those ring a bell to people, but there's dimensionality reduction things that let you look at complex data just on your computer screen. The one thing I'm going to talk about a little bit today is modeling nuisances. So in almost all scientific experiments, you have some aspects of the data you care about a lot, and some aspects of the data you don't care about at all. So if I go back to Large Hadron Collider, there's some channel you're looking at, there's a peak, which is the Higgs boson, and then there's a huge background rate of other events that you don't care about, that don't involve the Higgs boson. How do you model that background rate? So that's a place where people often use machine learning because that's a place where we don't care what's going on. We just want to model it. And then there's this thing of emulating simulations. If you have simulations, simulations are extremely expensive to run, or your partial differential equation solver or your ODE solver takes forever. You could do a small number and then use machine learning to figure out the rest. Good. So if you want to think about, I promise not all the slides are going to be laundry lists like this. This is just, I just want to establish some ground. There's many different ways to think about what machine learning is, and I'm going to give you a very general statement in a second, but most people think about machine learning in terms of specific examples. And the old school versions of machine learning, things that existed before I was a graduate student. So if you go way back, there's linear regression, principal components analysis, k-means clustering, and support vector machines. Those are the classical, those are the OG machine learning methods, and they still have very important roles in science. I've used all of those things in my research in the last few years. And one of the reasons they're so beautiful is they're very simple. You can understand them really, really well. And then there's the contemporary machine learning is things like Gaussian processes, which are like linear regressions where you've taken the number of features to infinity. That's what a Gaussian process is like, and we'll talk about that in a minute. Variational inference, which is a way to scale up inverse problems so that you can do immense inverse problems. Like if you have an inverse problem where you need to infer 1 billion variables, you need to think about that differently. And then, of course, deep learning, which is the rage. That's the thing that is the thing that's outperforming everything in image analysis and recommender systems and so on. And this is really an enormous zoo of methods, goes on and on. Okay, good. But now I want to take a conceptual view, what conceptually is going on, and want to talk a little bit philosophically, like philosophy of science here. So the idea, so a conceptual idea of machine learning is you have some data and you want to understand the relationships that exist in the data. And you don't care at all about the internals of your inference or your model. Your model is a black box that takes data in and predicts new data, but you don't really care what's going on inside the box. That, I think, is the conceptual idea behind machine learning. Now, if you go to the internets and ask, what's the definition of machine learning? There's a classical definition from the, 60s, which is that it is a machine learning method is a method that learns or improves as it sees more and more data. And that is somehow maps onto this definition in a weird way, but I will not discuss that. But so the thing I do want to discuss with machine learning is that machine learning takes all these machine learning methods take a very, very particular philosophical view of the world. And one piece of philosophy is the ontology of machine learning. So ontology is like what exists. And for machine learning, the only thing that exists is the data, or are the data. Is the data, are the data. Anyway, there's grammar issues, which I won't address. But the idea in machine learning is that there's only data, there's nothing but data. And one of the ways you know that is if you've ever used a deep learning model, if you've ever built a deep learning model and counted the parameters, you'll see that you have enormous numbers of parameters, way more than your data. And furthermore, if you have like fully connected layers, you have combinatoric degeneracies inside your model. So the machine learning models that are built, it's not just that people don't care what's inside. What's inside is so complicated, it's subject to unreal degeneracies, and it's not even comprehensible in principle. And then there's an epistemology aspect to machine learning. So that was the ontology. What's the epistemology? The epistemology is like, how do you know what you know? And the answer for machine learning is, if your model performs well on held out data, then it's a good model. There's no other criterion for deciding whether it's a good model. And notice how much that conflicts with our idea of science. We did not decide that general relativity should replace Newtonian mechanics because of its performance on held out data. That was not a consideration at all. In fact, no data were held out. Okay, good. So oddly, I'm going to say, so I think that epistemology, that ontology and epistemology is like very bad. So that's why, there's the bad for science. I'm going to basically say it's bad, but I have to comment that I'm actually more sympathetic to it than most physicists, because I'm not a realist. I say scientific realism here. I'm not a realist. I'm not sure that the laws of physics are correct. I think the laws of physics are effective theories. They're approximations to something that's correct. And so in that sense, if you look at science as a whole, maybe we do have a bit of the machine learning ontology in there somewhere. But people in the room would differ. Many people in the room believe that, quantum electrodynamics is correct. And some would say quantum electrodynamics is an approximation to some more correct theory. Fine. But I care deeply about the structure and content of physical law, and in that sense, I disagree with machine learning. Okay, good. So now, given that machine learning has these problems, where can we use it in our research? And so now what I want to do is go through places where the machine learning ontology and epistemology is good. It's what you want. And one great example, which actually Joao mentioned in my introduction, is that I love calibration, when you're calibrating an instrument. So if you're a scientist, you take data with instruments. Those instruments don't give you the answers you want. They give you some answers in device coordinates, and you need to transform those answers into the physical coordinates you care about. So for instance, if you take one of the telescopes here and point it at the sky and take an image, that image will be read out in pixels, but you want to know how that image maps onto the sky. That's a calibration of your image. That's what I would say is calibration. What's the relationship between the image read out and what's on the sky? And the thing that's interesting about calibration is that in many cases, you don't need to understand it at all. You just want it to do a good job of predicting new data. You calibrated your instrument last week, you calibrated it the week before, and now you want to know what's going to be the calibration of your instrument this week. And can you predict what the calibration of your instrument will be this week, given the calibrations that you took in previous weeks? So this is a perfect example for machine learning, and indeed, machine learning is doing extremely well. So I'm going to show you an example with a spectrograph. So the way a spectrograph works, if you're not, probably spectrographs exist across all of the natural sciences, so this is an example that everyone in the room should know something about, but you have light coming into your instrument, and it's dispersed by wavelength, and you want to know how the pixels in your device map onto wavelength. And the way you do that is you illuminate your device with some kind of lamp that produces light at known wavelengths, and you learn this relationship. Good? That's how we calibrate a spectrograph. But imagine you need to calibrate a spectrograph incredibly precisely. So the application I'm going to show you, well, I'm not really going to show you, I'm just going to talk about it, but the application that I'm going to talk about, we need to calibrate a spectrograph to a 10,000th of a pixel. We need to know the wavelength mapping so that it's good at the 1 part in 10,000 at the pixel level. So extremely, extremely precise calibration. And the way we do it is using old school machine learning. So we take, you have calibration data. These are data that have been sent into a spectrograph. That's light that's been sent into a spectrograph. It illuminates the device, and it puts lines on the spectrograph at particular wavelengths, known wavelengths. Actually, the system we're using is so beautiful. It involves a laser frequency comb. And if you don't know what a laser frequency comb is, beautiful thing. If you work on anything that involves optics, it could change your life, the laser frequency comb. Anyway, we illuminate the device with a laser frequency comb, so now we know all the wavelengths that are going into the device, and we get a map of where those lines hit. And we've done that thousands and thousands of times over the lifetime of this instrument. And then what we find is that when we look at all of those images, they actually live in a low-dimensional space. They don't span the arbitrary space of all things that could happen. The spectrograph is a physical device, and it has finite degrees of freedom. So in fact, the calibration data lives in a low-dimensional space. And then we take any new calibration image, and we map it into that calibration space. And then we do our interpolation to get our wavelength as a function of position, and we output a wavelength solution for every image. So this is a perfect example of how you might use machine learning in the natural sciences, because we don't care about the details of how the spectrograph optics are dispersing the light. We just need high performance. And you might think, if you're an instrument builder, you might think, that's crazy, you should figure out how it all works. That's true, you should, but no model of any spectrograph works to a 10,000th of a pixel. At a 10,000th of a pixel, everything matters. All sorts of temperature gradients matter. Actually, we found with this model, we could measure the rate of flow of cold water through the cooling system just by looking at the wavelength solution. Because all sorts of things matter in these problems. And indeed, this worked really well. We improved end-to-end Doppler shift measurement precision, and that's enabling the discovery of new planets. Not going to talk about anything exciting like planets. I'm going to talk about calibration. Okay, so I guess I'm not going to really tell you about my lab, but I will tell you about what kind of things we work on machine learning. Is there anything I want to say back here? I guess one thing I'll say about my lab is, though we work on machine learning, and Joao said that people use our methods in astronomy, one of the reasons people use our methods in astronomy is because we are focused on very, very simple models. We work with machine learning systems, but we try to make very simple ones that are understandable. So we're not in the business of making very deep networks, but we are in the business of using those OG machine learning methods that I liked so much at the beginning. And we do a lot of training and workforce, and I was honored that you mentioned that in the introduction. Okay, good. What do I do in machine learning and astrophysics? I do calibration of imagers and spectrographs. And in fact, that's how I really got into machine learning in the first place. We had the Sloan Digital Sky Survey imaging, and we built a coherent calibration model of that. And we realized we didn't know how to do it. And we talked to our computer science colleagues. So it was an example of interdisciplinary data science, because we couldn't even figure out how to do the problem on computers that were available at that time. And that's how I got started in machine learning. We do data-driven models for stellar spectroscopy. I'll show you that in a minute. We find planets around other stars, both in spectrographs, like I just mentioned, and also through transits. And we use machine learning to model variability of the stars. I'm going to show you that in a second. And then I've been doing some applied math things where we try to implement exact group theoretic symmetries in machine learning models, and I'll show you some words related to that. Okay, good. So classic machine learning task, I already mentioned this is like kittens. You have many features. So features in machine learning are what you would naturally call the data. Features would be, in the case of the kittens example, your features Y would be the entire YouTube video, would be your features. In the case of that instrument calibration, it would be those images that we had from the spectrograph. And then the labels, and then there's labels X. In the case of classification, you have categorical labels. They're like integers. And then in the case of regression, those labels will be real valued labels. Regression is when you're trying to measure a quantity. And in the natural sciences, we do a lot more, I think, measuring of real valued quantities than we do of categorical classification. So I think this is kind of a more interesting setting for machine learning. We want to find the function f of y that predicts x, the function of the features that produce the label. By the way, I don't know why I used x and y in this thing. Now I would put them the other way around. I don't know why I did that. Anyway, I mean, I was enjoying Viennese beer and wine last night. Okay, good. Good. One very important idea in machine learning, actually, so I tend to make it sound like machine learning people are incredibly cavalier. They don't care about what's inside their model. They just try and reproduce the data and whatever. You know, I tend to sound like that, but I don't want to sound like that because there's a very important idea in machine learning that the sciences could adopt, which is this train, validate, and test. And we do not usually, as scientists, we do not usually split our data into train, validate, and test. And there's a lot of reasons that's a good idea. Like I mentioned that when we adopted general relativity over Newtonian mechanics, it wasn't because we predicted held-out data. There were no held-out data. It would have been better if there were. There would have been some questions that could have been answered better if there were. And this is related to blinding in physics projects and hypothesis registration in statistics, which are all like important ideas. So I think I personally have learned a lot about kind of statistical rigor from the machine learning community, even at the same time that I've been making fun of them for being so cavalier. But almost no natural science problems fall into this standard regression form. Why not? So this is so now switching back. Now I'm getting mad at machine learning again. Why? Because first of all, we rarely have labels that we truly believe. I mean, it depends what science you're in. If you're in chemistry, you can repeat an experiment over and over again, and you can be sure that you have your labels correctly. But in astronomy, we don't get to do that. In astronomy, the light happens to fall on the telescope, and we get the measurements we get. And we argue, you know, there's a big argument in astronomy about the oxygen abundance of the sun. Sun's not that far away. Most things we observe are way farther away than the sun. But there's no way we can go to the sun and grab a piece of the sun and check its oxygen abundance. That's why it's an argument. And so in many cases, we don't have labels we truly believe. And often when I'm interacting with machine learning people, they're like, oh, well, in this problem, what's your ground truth? And I'm like, what do you mean? And they're like, what do you mean? And then I'm like, it's astronomy, there's no ground truth. And then they're like, I don't believe anything that's ever happened in astronomy then. And I have to say, that's the talk I really want to give. How do we know things in astronomy given that there's no ground truth? We can't even get a sample back from the sun. And yet we know very confidently what the stars are made of, what their lifetimes look like. We know the universe is expanding. We know the age of the universe to 4 decimal places of accuracy. When we have, anyway, great subject. Good. Now, another reason this standard regression form doesn't work for astronomy and for most of the sciences is the data that we care about are never drawn from the same distribution as the data we trained on. For instance, when I'm doing an astronomy thing, I've found some nearby stars. Now I want to look at the more distant stars. The more distant stars have different noise properties, and they're drawn from a different distribution than the more nearby stars. So this train and test framework doesn't really exist in most science problems. You found the ocean life at one depth. That won't give you won't give you that great a prediction about the ocean life at a much greater depth. And then, of course, we care about understanding and insight. And I will talk about this later, that we also have very strong beliefs about how scientific laws work or how the world works. And so for all these reasons, this kind of very generic machine learning is not really scientific. And here's a thought example, like a thought experiment, just to give you a sense of why I think it's wrong. But this will mean more to the astronomers in the room than everyone else. But imagine I'm trying to find all the planets in some data set. And the way I find the planets is I take a little bit of the data and I search for planets in the way we usually do, which is by fitting physical models of stars and planets to the data. So we fit the physical models and we get a list of planets. So we have stars that have planets and stars where we don't know. Actually, it's very much the one classification problem that Sebastian Rutzenbach just defended his PhD on yesterday. You would have a bunch of stars where you can see that they have planets, and then you have a bunch of stars where don't seem to have planets. Now, then I could just train a deep neural network to find all the other planets. Would that be a good idea? Actually, multiple undergrads have come into my office and proposed this. They're like, we use machine learning to find all the planets. I'm like, okay, good, but let's talk about it for a minute. And one of the reasons that this is not a good idea is that if you did find planets this way, you'd have to verify them by running the physical model that you used to search for the first ones in the first place, in which case, why not just find them all with that physical model? Second of all, you can think of the edge cases. Imagine things the physical model found that the machine learning didn't. That would be a failure of the machine learning. Think of something that the physical model didn't verify that the machine learning found. That would also be a failure of the machine learning. Machine learning loses in all cases. However, we do, in fact, now use tons of machine learning when we look for planets. But it's not in that form. We use it in a different form. We use machine learning to calibrate or to build a noise model for all the crazy things that happen in the data that aren't planets. See, so we don't use machine learning to find the planets. We use machine learning to capture all the things in the data that we don't care about, of which there's a lot. I think I have an example. Yes. So here's an example. So this is from a NASA mission called K2. These data are from K2, and these are a couple of papers which you can get off that link if you want. But what is this? This is a time coordinate. Astronomers use very strange times, which I will not explain. This is a time coordinate in days, and each dot is like a measurement of the brightness of a star. And you can see there's the top, there's the brightness of the star as a function of time. It's doing some crazy thing. And then if you look carefully, there's a green line drawn through those points. That green line is a machine learning prediction of what that star ought to be doing. And that was made not using that star. This is held out. So this is true train and test. So we trained on other data and we predicted the behavior of that star. How is it that we can predict the behavior of that star so accurately? It's because that star's behavior is dominated by spacecraft issues. This is a NASA spacecraft that was in an Earth-trailing orbit, and it was being illuminated by the sun and firing thrusters, and every time it got fired its thruster, it changed the illumination from the sun and changed its temperature profile, changed the spot pointing on the CCD. Anyway, all sorts of crazy things happen, which cause it to have this crazy pattern. And if you're an astronomer, I can go on at length about why the pattern there looks like the inverse of the pattern there. Beautiful things, but I'm not going to talk about that. But notice that when we correct for that prediction, we get a much, much better measurement of the brightness of the star. And there's different scales here. This measurement is good enough that you can see planet transits. And in fact, we discovered some planet transits this way. So this was a data set where people didn't know how to discover the transits because the data was too ugly, although that data is still pretty amazing. That's parts per million, 2,000 parts per million. We're measuring a star's brightness to a part in 1,000 or a few parts in 1,000. Not good enough. To find planets, you have to measure to tens of parts per million to find planets. But this is an example of using machine learning to find planets. It's not that the machine learning tells us where the planets are. The machine learning tells us what the star is doing that isn't planets, the part of the problem I don't care about. There's other people in the room that do care about that, but I don't. Okay, good. I said all of those things. Okay, good. So there's very interesting, one thing that I think is super exciting about the introduction of machine learning into the sciences is we've been learning a lot of statistics. I already mentioned the train, validate, and test concept, which I could have put on this slide as well, but there's other ideas from statistics coming in. One idea that I think is really important is this idea that data analysis problems have hierarchical structure. What do I mean by that? Like, how did we figure out this model? How did we make such a beautiful predictive model for this star? It was by looking at all the other stars. And because all the other stars are observed by the same spacecraft, they all share information among them about the spacecraft. And so by capitalizing on the fact that they all share information about the spacecraft, the other stars can be used to predict what this star is doing. That's called hierarchical structure in statistics, and sometimes there's a literature in statistics which uses the word denoising, which has to do with the same thing. How do you get in information from other objects? And this is generic in the sciences, and it hasn't been thought about enough. In a lot of contexts in science, we're ignoring this hierarchical structure. It's incredibly valuable. And then there's, I've mentioned momentarily that some of the models have more parameters than data. I mentioned the Gaussian processes are like infinite number of parameters. Let me talk about that for a minute. This is something that's been known in statistics for a while. I only learned about this during the pandemic. So this is very new to me, and I was surprised that I didn't know it. So I've been dining out with astronomers, asking them if they know this. And it's definitely new for us. It might be less new in other sciences. Okay, so here's something that I learned when I was a wee child, which is that if you're fitting data, so you're fitting some data and you have some capacity, you can think of this as like the number of parameters in your model. Imagine you're doing a fit of sines and cosines. You're fitting some signal with sines and cosines. You're using a small number of sines and cosines. You're using lots of sines and cosines. This is like the number of free parameters you have in your model. It's called capacity for technical reasons, because sometimes you don't figure out your capacity by counting your parameters. Your capacity could be set by the strength of a regularization or something like that. But anyway, let's think of it as the number of parameters for now. So if you fit with too few parameters, what's this black line? Statisticians call it risk. What it means is just how well you are doing on held out data. It's just a theoretical version of how well you're doing on held out data. It's slightly more complicated than that. It's an expectation value, but whatever. So think of the black line as plotting how well you do on held out data. If you have too little capacity in your model, you don't do a good job of predicting held out data because you just don't have enough flexibility to capture it. And then as you increase your capacity, you do better and better. And then if you increase it too much, you start to do poorly again. And there's a sweet spot, which is the best place to work. And in particular, if you go to the capacity such that you have as many parameters as you have data, things usually blow up. You can't predict anything. There's degeneracies. Okay? Make sense? That's literally what I was taught the first time I ever did a data analysis. You can't have more parameters than data. There's a correct number of parameters. You can find it by holding out data, cross-validation, whatever. Good. Everyone good? Turns out that's all wrong. It's wrong. You can keep going past this threshold and you get good models again. And the models over here often beat the models over there. I mean, I dropped the mic, I'm out. For who here is that a new thing? Oh, good. Quite a few of you. Good. I'm not totally wasting your time. Okay, now, I have a million things to say about this. The proofs for this are all in the situation of linear regression. Linear regression is where this is proven, but it actually applies, empirically it applies to all kinds of models. It applies to deep networks. It applies to everything that people have looked at some level. But it's a little bit hard to write down what this is, and it's complicated. But one of the things you might notice is that if you're doing linear regression and you have more parameters than you have data, you have infinite degeneracies. Your model becomes degenerate. So you do have to break those degeneracies somehow. But this curve is generically true however you break those degeneracies. It's weird. Okay? So now, one thing, some of you implicitly already know this, because some of you were doing something using a polynomial fit and then switched over to using a Gaussian process. When you switched from doing a polynomial fit, where you were trying to find this location, to using a Gaussian process, you actually took the limit of infinite model capacity. A Gaussian process can hit any data you give it. It has infinite capacity, and it works beautifully. And often Gaussian processes outperform linear regressions. So many of you have actually experienced this without kind of unconsciously, without thinking of it. So actually what I should ask, but I'm not going to, it's who here has used the Gaussian process but hasn't seen that. But anyway, I won't ask that. Because that was me 18 months ago. I had never seen that, and I was happily using Gaussian processes. It had never occurred to me that a Gaussian process has infinite capacity, and so it shouldn't work. Anyway. Okay, good. That's just an aside just to say there's some beautiful things going on at the intersection of math, statistics, and computer science. And I hope I put a reference on that. Oh, I just put this. This is from an explainer by Ahuja. But there's some beautiful papers that has that explainer, which you can find on the internet. It's just an internet explainer, but it has links out to the papers where the proofs are. The proofs are gorgeous. It's beautiful things. Okay, good. Oh yeah, back to the story. So one place where I think machine learning has been really successful in the sciences, and I think it will continue to be so, is dimensionality reduction. In fact, that was PCA, principal components analysis. Like, you can look through all the literatures, all the natural science literatures, and you can see the moment that PCA gets introduced. Because it's just like, boom, there's a step change in what people are working on. And in astronomy, that happened around 89. Around then, principal component analysis was used to look at galaxy spectra, and then boom, all of a sudden, everything involved principal components analysis, just step change. Because all natural science targets live in a low-dimensional space of their data space. It's just absolutely generic. And this is the basis of a lot of things, that Excalibur calibration method I gave you. I'll just flash another example. This is a model for stellar spectra called the Cannon, which is named after a very important person, not a weapon. And I don't know if you can see it from back in the room, but every one of those panels has a black line, which is data on a star that was not in our training set. And every one of those panels has a cyan band, which is our prediction for that star's spectrum. And you can see that this, which was trained on only a few hundred stars, beautifully predicts all of the absorption lines and continuum of all these stars, which are different metallicities and different temperatures. If you're a solid astronomer, you can see there's a temperature difference there and a metallicity difference there, but don't worry about that. But these are, the point is that it took very little training data to build this low-dimensional model of spectra, because stars just aren't that complicated. They look complicated, but from a data perspective, they're not that complicated. Now, the physical model that predicts these spectra actually also does pretty well, and to be fair, I should also put it up because there's a physical model that does pretty well, but not as well. And that model is very big and very slow. In fact, because it's a big PDE solver with a very large number of terms, because each of these lines is from some atomic or molecular transition. So it's a very, very complicated partial differential equation. So anyway, I'm not going to talk more about the Cannon, but I just want to say that the Cannon replaced a component. Apogee is part of the Sloan Digital Sky Surveys, which Joel mentioned, and we replaced a part of the pipeline that takes CPU years with something that takes CPU minutes. So we went from running on a huge data center for months to running on our laptop. And so that's a good example of where machine learning can really speed things up. But I should say, we're doing these parameter inferences, and the question is, are they believable? And we don't have ground truth. And of course, the sample we're training on is not quite the same as the sample we're running on, and all the things I just mentioned. So there's a lot of question marks here, but it's fast. Right? But you know, that's how a lot of things go in machine learning, right? They're like, but look at the speed. You're like, but what about, and look how fast it is. Okay, good. Good. Okay, now, how am I doing? Great. I'm doing great? Yeah. Okay, good. I'm glad. I like the word great because it doesn't have a time in it. Okay, good. Now, so I'm like a quarter of the way in. No, I'm kidding. No. Okay, so one of the things that's been very interesting in the natural sciences, and I now think this is true in all the natural sciences, is that now theory is a simulation. I should have written an equation here, because like physicists like to think that physicists love it. Like if you say, oh, what's general relativity? And they write like T mu nu equals 8 pi over C cubed or something, G mu nu. They write an equation like this that is like this big. And then they're like, oh, good, that means physics must be really simple, because that little simple equation. And of course, if you actually want to compute anything in general relativity, you have to do an immense calculation. In fact, there's some of the biggest numerical calculations that are being done in the world right now are general relativity calculations to support LIGO mission and in spirals of black holes. So the theory of black hole mergers is simulations. There is no pencil and paper theory of black hole mergers anymore. When there was, but it wasn't very accurate. Similarly, climate. Think about the climate model. It's true that global warming was understood back in the 1800s. In principle, it was understood that there must be global warming. It will happen with industrialization. That was understood early. But the global circulation model is an extremely expensive computation that knows a lot about the Earth and a lot about the atmosphere and a lot about the oceans. So basically, we no longer are comparing it's no longer like measuring the expansion of the universe where you fit a line through some data and then the slope of that line is the answer. That doesn't look like that anymore. Now, we are really doing things with immense simulations. And I think I'm a little more specific here. Yes, good. So what does it mean when your theory is a simulation? Well, if your theory is a simulation, now you're trying to find simulations that look like your data. That's what people are doing in most of the natural sciences now. And there's various things you may have heard of or even used: likelihood-free inference, approximate Bayesian computation. These are simulation-based methods for doing inferences or for learning about the world. And they generally involve an immense amount of computation. So a typical large-scale structure simulation that we use in cosmology takes a CPU year. So if you are trying to do many simulations to find simulations that look like the data you are seeing, you're talking about many, many CPU years, like hundreds of thousands. And then you're getting into the regime where you need to say what your carbon footprint is when you publish your papers, right? Because you're searching in some immense space of initial conditions. So there's a hope that's emerging right now in machine learning and the natural sciences, which I'm excited about, but I'm going to be a bit negative on, which is that you do some simulations, and now you treat that like a regression. So you treat it like the initial conditions. Now I've swapped X and Y back to where I want them. But your initial conditions are like your features, and then the final state is like your label. And the final state is the whole state of the world. So it's the initial conditions of the world. You run a simulation, you get the final conditions of the world. That's your label. This was your features. Now learn the relationship, machine learning. And this has been demonstrated to work really well in cosmology in particular. Here's an example. These are not supposed to match pixel for pixel. They're supposed to have the same statistics. This is a simulation of the density field that was outrageously expensive for a chunk of the universe. And this is a simulation of the density. This is not a simulation of the density field. This is a prediction from a model, a machine learning model for the same thing. And the paper that this is just one of many papers. There's probably 30 papers on this subject now. But this paper shows that the statistics of this prediction are beautiful, and it looks just like the universe in all respects. So one thing that can go wrong, I don't know if you've seen this paper before. This is a very famous image from the internets, and I love this image. But I love it for a very technical reason. I mean, it's cute. But so this is an image from one of the standard ImageNet type databases, I don't know which one, that some system, this is a long time ago. This is from 2015, which in machine learning terms is like, I don't know, like it doesn't exist. But anyway, like if you count time in number of papers published, this is probably like in the first 0.01% of machine learning's lifetime. But anyway, basically in this paper, they trained a very successful deep learning system that could label images very accurately. So here, this image was said to be a panda. I hope you can see that and see that that's a panda. Anyway, and then they carefully designed extremely specific, very weird noise fields. So they add this carefully designed noise field to get that image. See how different that image looks from that image? Not at all different. And yet, the same network then calls this a gibbon. Okay, now, there is a huge literature about this, which I am not going to summarize. I take from this one thing, and exactly one thing, which is that this machine learning method looks like it's emulating a human, right? Because it shows that image and says, that's a panda. But it is definitely not emulating a human, because it looks at that image and says, totally different. That's a gibbon. And that shows you that the machine learning method isn't doing what you think it's doing. It might be doing something great, it might be doing something correct, but it is not doing what you think it's doing. It's not identifying black spots around eyes in a white fuzzy face. Although gibbons have some of that too. But anyway, it's not surprising that it's a gibbon. It would be harder to get flamingo out of this. And part of the reason, I think, is that these methods are very sensitive to pixel histogram, and so tiny changes to the pixel histogram, I don't know. I don't actually understand why, but the important thing from my perspective is this shows that when you think you're emulating a system, you're not necessarily. Good, so I say deep epistemological problems. It's not really a deep epistemological problem because that machine learning method worked very well on held out test data. It just didn't work well when we punked it. See? So here's another thought experiment. Here's my second thought experiment. Imagine we build machine learning into our simulation-based inferences. We do lots of cosmology, and now for the cosmologists, we find something extremely important. Like we find primordial non-Gaussianity. We find that the expansion history has some anomaly in it. We find that the neutrinos have negative masses. Like imagine we find something really important with our machine learning-based pipelines. Well, guess what happens? A whole bunch of physics theorists write papers. And then some graduate student says, but wasn't there a lot of machine learning involved? Maybe there's a mistake. And now you can ask, how would we verify the discovery? Well, one way you might verify the discovery is just redo it with full simulations, with complete simulations. Just redo it. But by construction, you can't. The simulations are too expensive. Every simulation takes a CPU year. You don't have the resources, or maybe you don't even have the carbon footprint. Also, there's this problem of confirmation bias. You're only going to check it when it shows you something you didn't expect. That could be ruinous to the sciences. That could truly be the disaster for the sciences. Okay, good. So my hope, and I'm just going to show you a few slides of this and then I'm out, is that my hope is that we could make machine learning methods that look more like physical law. And if the machine learning method was more like physical law, we could more believe that what it was doing was believable from the context of physical law. And so we're interested in exact symmetries. there's like too much here, but here's a toy problem people use in machine learning sometimes, the double pendulum. It's classically chaotic, it's fun, you can't predict very far into the future with it because it's classically chaotic. We currently have the best in the world predictions for this model, for this toy problem, because we can build exact symmetries into our machine learning methods. And I think I talk about, yeah, well, the two things we're basically putting in are exact geometric symmetries like rotation and translation and permutation and all those symmetries that you believe exist, unitarity, boost if you're a special relativist, and then dimensional analysis. Physical quantities have dimensions, they can only be combined in certain forms, so we're sort of building machine learning methods that exactly respect these behaviors, and when we apply them, we now have the world leading on some toy problems that nobody cares about. And there's similar things you could say about causal structure. So we believe when you observe a star, the light from the star was emitted by a photosphere, went through the interstellar medium, then went through the atmosphere of the Earth, then bounced off some optics, and then hit a CCD. Since we believe there's that causal structure should somehow exist in the machine learning methods we're using. If it doesn't, some kind of mistake is being made. So I have one last thing to say before I go, because I've sounded like I'm saying, oh, it's so cavalier, people are using machine learning, and they're like, hey, check out how fast it is. But there are moments, and we were talking about this at dinner last night, there are moments where machine learning can be the conservative choice. It can be more conservative to use a crazy machine learning method than to use your best ideas. You're like, how could it be conservative to just throw a black box at it? Well, if you think about causal inference, the problem with causal inference, does this cause that, is you have to be worried about there being confounders. And you want to be as flexible as possible with your confounders to believe your causal inference. So in the case of planets, it's very simple. If the extremely flexible model I learned with my machine learning cannot possibly explain the planetary signal, that actually gives me more confidence in the planetary signal. I can say I threw every black box I have at this, and I couldn't explain that signal without also adding a planet. That actually increases my confidence that there's a planet. So you can actually, it's like punking the machine learning problem. You take the problem with machine learning, use it to your advantage. And this is used a lot in statistics in causal inference. When people are trying to understand, does this drug cure this disease? Often the confounding model is being modeled with machine learning methods because they want the most flexible thing they can have to catch the confounders. That's what I said. I'm done. Thank you.
So thank you very much for this amazing talk. And we're going to have some questions, and I'll ask anyone for questions now.
Don't be shy.
It's too impressive. Everybody's shy.
That's what I wanted to say. I'm very impressed. I just want to say I'm extremely impressed because you touched some really basic problems. I mean, I did a lot of physical modeling, a bit of machine learning, and as you said, also the physical laws are sometimes assumptions. I mean, we usually use the heat equation, but in reality, heat transfer is a hyperbolic problem. So we do approximations everywhere. Is the squaring of the distance the real thing in gravity? We don't know precisely.
That's right.
So I think your view of combining, for instance here, what you have, discover low-dimensional structure. So combining, and that's also the idea, the basic idea, behind our network, to combine both worlds in a flexible way, and I think you gave a lot of input to this.
Oh, good, thank you. Yeah, I think one of the reasons we were inspired to do this kind of physics-inspired machine learning where we're trying to make things have the same structure as physical law is because when we find the low-dimensional structure, we want to find it in a way that can be explained in terms of, say, invariance or scalars or... and so I think, yeah, I think it's very exciting.
So I have a more technical question, I think.
Hit me.
So when you mentioned that the problem with adversarial examples and so on, I mean, this is really specific to neural networks, and one cannot really avoid it with neural networks. So when you say machine learning, you mean, I mean, because to me this would call for understanding better how to build different models that are not as flexible as neural networks, where one can avoid this type of instabilities.
Good, that's a good technical question. I actually said something a little aggressive. Let me see. I tried not to be controversial, but where was I talking about it? Check it out. So my claim is that all methods are susceptible to adversarial attacks at some level. Now, it is true that if data are fairly low dimensional and your model capacity is fairly low, there isn't much room for adversarial attacks. The reason that deep networks are so susceptible is there's so much capacity in a neural network. It's absurd how much capacity, way more than you need. In fact, they deliberately overcapacity the objects because they're relying on this double descent. So there's actually a, what was I going to say? We wrote a little note here about this problem, and in that note we talk about the fact that when you get into this regime, though it is true that you perform well, you also become susceptible to adversarial attacks, even in linear regression. So, I won't agree with you, but I will agree with you that certain things are very good. Like Gaussian processes, you have this kernel choice. You really know that it cannot put structure in your problem below some scale, and that is very important. So I think I agree with your kind of meta point that what is attackable and how is going to be a very strong function of your method choice. I agree.
Glenn.
Yes, so thanks a lot.
Hey, Glenn.
Hi, nice to see you. So I'm not going to talk about the overfitting problem, as you know, with the Swatchy model, etc. But I was wondering, so it was really great to see that what you put out is to use the machine learning to principally filter out what you don't care about, what is not your main problem. But can you give an idea, for example, when you were fitting this exoplanet data, how can you ensure that you don't also then kill the signal that you want? What kind of statistics or what kind of approach can we use?
Yeah, you ask a great question. So there's different, so the papers that are cited up there do actually extremely different things. This figure is from the second one, where we are relying, the data set's not that big, and we're just relying on there not being enough planet signals in it that the machine learning method will learn planet signals and take them out too. So it's kind of like the one class problem. You just assume that most things are not in your class. So that one is, and this is susceptible to that. So in principle, we might be pulling out some signals. In the former paper, we do something we have much more data, and so we do a censoring, not just that we don't use this object when we build our model, but we also don't use, if we're looking at an exoplanet transit at this location, we don't use this time either. And so we build a model that can't be poisoned by certain kinds of signals. So there's no really generic answer to your question, of course. Everything you have to think about it specifically, but you're asking a very good question, which is, if I wanted to rephrase it, I would say, how do you stop leakage of the signals that you care about into the model that you're removing? And the answer is very problem specific, I think. I don't think there's an extremely, we do basically do it with train and test, but you have to select very carefully how you cut in train and test.
Yeah, because one way to solve it, we're trying to make mock data, but you can never make your mock data to be as good as your real observed data. So but at least for certain parts, you can then have the ground truth between codes.
Yeah.
Yes.
No, and indeed, the way we tested these methods was by inserting false transits. But of course, as you just said, your model, your simulations of the transits will never be as accurate as the transits. And so, yeah, that's always, and that is, and frankly, that's why I was saying it's conservative to use the machine learning, because you'll tend to underreport discoveries. So though I agree that's a problem, it tends to hurt you in the conservative direction.
Gwenel.
Thank you. I do want to ask a question about the overfitting, actually.
Yeah.
So when we look at...
don't know which way it is now.
Yeah. So when we look at these big neural networks, then we are in the first part, because at some point you do get worse in a lot of these cases.
Well, I mean, the really big things like that Facebook's running are way over here, or DeepMind are way over there. Like AlphaFold, which was mentioned in the introduction, is way over there.
Mm-hmm. And is this really just a matter of adding more and more parameters, or is it also a kind of, like you mentioned with going to Gaussian processes, where we just need to like find another clever way of looking at it that might not require as much hardware and throwing more RAM at it?
Good. So I didn't talk about the kernel trick. And it would be very interesting to talk. So one thing that threads through all of machine learning is this concept of the kernel trick. And the kernel trick is something that allows you to work at infinite dimensions with finite computing. And it has to do with an important idea in physics, which is that you can take dot products between infinite dimensional vectors in certain cases. If your metric has certain properties, you can take dot products of very large vectors. And there's lots of beautiful math around that, beautiful math and physics around that, so it's very nice. And that allows you to work at infinite dimensions. With deep learning, people increase the capacity by basically adding depth, adding layers to their network is the main way people increase capacity. But if you have, where does the kernel trick work? It works in problems that look super linear, like PCA, there's kernel PCA, SVM, support vector machine, there's kernels SVM, linear regression, there's Gaussian process. Those are three methods that involve they're very much linear operations. They're built on dot products of vectors. But if you don't have dot products of vectors, basically your model just gets huge. I don't think there's any way to do it. Right now, there's lots of room for new math. I hope there's some mathematicians in the room.
Question in the back? It's on, it's on.
Interesting talk. Can you go to the panda picture?
Yeah.
There's a growing body of work for investigating black box models, collectively called explainable AI. And one of the methods is called LIME. There's a few methods, but that's the easiest one to explain here, which would pick out in your panda picture which of the pixels were the most responsible for predicting panda.
Yeah.
And with the same rationale you'd see with the gibbon, which pixels were the ones that were causing that confusion. It's just, I think, important to know about.
Yes, absolutely. And let me just say a few more words about that. So I tend to make fun of deep learning methods as being like totally incomprehensible objects, which is fun and all. But as you point out, these models are built with some very beautiful properties. And one of the beautiful properties is that the models are fully differentiable, meaning you can take all the derivatives you want from the output to the input and vice versa. And if you think about information theory, or if you think about discrimination or anything you want to think about, the derivatives of the model are all computable, which means you can actually draw a line between gibbon and panda and ask moving what pixels takes you along that line. And that's, of course, how they found this. So this is very related to explainability, because they use the fact that the model can be understood in that way to construct this. And so I think that's a very insightful comment, that there's a lot of work going on to understand these models, and that the adversarial attacks are kind of using the same technology that the understanding is using. And so that's why I think this is so important from an epistemology point of view, because it gets at what does the model mean? Which I think is much more interesting, and maybe that's where I'm kind of trying to say we should be moving in that direction. So I agree with that completely.
Hi, David. I'd like to maybe challenge this distinction you've made between being comfortable with using machine learning to model the noise or nuisances compared to the physical signal. Mm-hmm. So you touched on this yourself.
Yeah.
Light curves, someone else is interested in the stellar variability.
Yes. Yeah.
So, I mean, is there a real distinction there, or is it arbitrary?
I don't know. I mean, you're pushing on the weakest part of the weakest part of my story is this point that it can be conservative to use it in some places when it's not at all conservative to use it in others. And but I think so. I don't have an answer for you. The only thing I can say is and this is kind of let me step back one step. Physicists like to think that they are the keepers of objective reality. That like we are the people who observe and understand the universe and deliver objectively the results of how the universe is. And we're priests. You can ask me, how a black hole works, and I will explain to you. But every scientific investigation is a subjective set of choices that we made with our own subjective goals in hand. And what you're going to use your machine learning for really depends on those subjective choices. And so we wanted to find the exoplanets. We did not care at all about the spacecraft variability. And somebody might have taken our results and said, oh, that's a great model for spacecraft variability. And we would have been like, no, it's not. Because that was not our goal. So one of the things that I think is super interesting about all this is it really reveals the subjectivity of the work we do. The components of my model are based on my desires and my interests, not in some sense like on an objective classification of the world into spacecraft and star and planet. How's that for not answering your question?
I'm satisfied.
Okay, I think maybe it's time to thank Dave for this brilliant talk.